Hey guys, another key concept for today is this, the fundamental counting principle, which is in your book in section 10.1 if you want to look it up. But this is what it says. If there are m ways one event can occur, and n ways that another event can occur, then there are m times n, so that's not an x, it's a multiply. There are m times n ways for both events to occur. So we're going to do a couple examples here, but let's start out with this one. And we're also going to make what's called a tree diagram. Which kind of goes along with this. So fundamental counting principle and tree diagrams kind of go together. So how many outfits can you make from 5 shirts and 3 pairs of pants? Well, you might already know the answer to this, and if you do, awesome. I want to show you how to make a tree diagram though, because sometimes situations can get more complicated and it's nice to be able to visualize. So what we're going to do is we're going to start out by listing out the 5 shirts that we can choose. Okay? So when you do a tree diagram, you start with kind of a point there, and from this point we have a choice. We have 5 different choices of shirts. Now we could choose our pants first, that's okay, it would work that way, but since it's talking about shirts first, we can do it that way. So what we're going to do is we're going to basically branch out. So think of this, I don't know if you guys remember these, but way back in the day they had these books called Choose Your Own Adventure books, and you're reading and you're like, you're in a cave, and you come to a fork in the road, and you decide to go left or right. If you want to go on the left tunnel, turn to page 56. If you want to go on the right tunnel, turn to page 99, and then you'll have different options. So that's kind of what this is. We're like making a choice here. So we have 5 different paths that we can take, 5 different choices that we can make. So we have shirt 1, shirt 2, shirt 3, shirt 4, and shirt 5. And of course, because you're a mathematician, all of your shirts are numbered. They just have numbers on them, and that's how you roll. Okay? So let's say that we took the first branch. Let's say we chose shirt 1, right? Well, now we have a second choice, and that second choice is we can choose from a lot of different pairs, one of 3 different pairs of pants. So if I made this choice, I still have 3 different choices to make for pants. Now I'm going to abbreviate because I don't want to write pants this many times. So I'm going to say pants 1, pants 2, and pants 3. Right? But I have that same option. So that if I choose shirt 1, I have these different options, right? But let's go back and say, well, what if I chose shirt 2? I still have those same 3 choices of pants. P1, P2, or P3. Right? But let's say I chose shirt 3. I could have chose P1, P2, or P3. Right? So this is getting a little cramped. We probably should have spaced this out a little bit better. But you get the idea. P1, P2, P3, P1, P2, P3. So the idea is for each shirt choice, I have 3 choices. And so what you end up seeing is you see 5 groups of 3. Right? Here's 3, here's 3, here's 3, here's 3, here's 3. There's 5 groups of 3 pant choices, because there's 5 shirts. So 5 groups of 3 is 5 times 3, right? That's 15. And if you count out how many options there are, well, this is an outcome, this is an outcome. These are all different outcomes. So shirt 1, pants 1. Shirt 1, pants 2. Shirt 1, pants 3. Those are 3 different outcomes, right? Now this pants 1 is different from this pants 1 because this outcome represents the choice that I made shirt 1 first, and then I chose pants 1. So this is shirt 2, pants 1. Shirt 2, pants 2. Shirt 2, pants 3. Right, there's 3 of those. There's also 3 options if I choose shirt 3. I can choose this outfit where I have shirt 3 and pants 1. Or I could do shirt 3 and pants 2. Or I could do shirt 3 and pants 3. And these are different outfits than these ones because they don't just represent pants 1, it represents pants also coming off of the shirt 3 branch, which means this is shirt 3, pants 1. Right? Or I could do shirt 4, pants 1. Shirt 4, pants 2, shirt 4, pants 3. There's 3 options for shirt 4, and so on. Okay? So all of these different circled things here is a different outcome. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of those. Right? Again, 5 groups of 3. 5 different shirt options, but for each choice there, we have 3 different pants options. Okay, so if you just, the two events here are choosing a shirt and choosing a pair of pants. There's 5 ways to choose a shirt, and there's 3 ways to choose a pair of pants. So there's 15 different possible outfits that you can have. Okay, you can also do this with numbers and codes and stuff. So, how many codes can you make? Let's do how many 4-digit codes? Can you make? And let's make these numerical. Okay, so if you don't already, one day you might have a credit card or a debit card, and for that credit card or debit card, you are going to have a PIN number. And that PIN number will be a 4-digit code usually that you type in that will give you access to your account. So the idea here is if you have a 4-digit code, how many ways are there to do that? Well, we have to think about digits. How many digits are there? If you're going to choose a digit, there's really only 10 options. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. You can't choose 10 as a digit because that's 2 digits, right? You can't choose 11 because, again, that's 2 digits. There's only 10 digits you can choose from, okay? So the idea here is if we have a bunch of events occurring. Okay, the events we have occurring is basically choosing a number for the first digit. So how many different ways are there to choose the first digit? Well, there's 10 options, right? So that's event 1. Okay, this says if there are n ways an event can occur and n ways another event can occur, then there's n times n ways for both of them to occur. So how many ways are there for me to choose a digit? There's 10. How many ways are there to choose a second digit? There's also 10. How many ways are there to choose a third digit? So now we're adding another event, right? So you would call this event MNLO, right? Well, if we have an event O, then there's going to be n times O ways for that to happen. There's going to be 10 digits there, right? And 10 digits there. So each time I choose a number, there's 10 ways for me to do that, right? So if I want to know how many ways there are total, it's 10 times 10 times 10 times 10, which would be 1, 2, 3, 4, 10,000. There's 10,000 different ways you can choose a PIN number, okay? Now we could try to make a tree diagram for this, but it was going to be crazy. So let me demonstrate what that would look like. You would have your digits, right? This would, the first branch would be like choosing your first digit. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Okay? And then off of this one, you'd have to draw 10 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And off this one, you have to draw 10. Off this one, you have to draw 10. Alright, so back here, you draw, and then off of each of these, you'd have to draw 10. And then off each of those, you'd have to draw 10. So you have this like branching, and it's crazy. It gets out of hand really quick. So we can start with a simple idea like, 5 and 3, multiply and get 15. But this fundamental counting principle extends to more events and more options than you could keep track of with a table, or a tree diagram. So fundamental counting principle works for multiple events. And the idea that you have to think about is choosing a digit or selecting a digit or something like that you can think of as an event. And you gotta know there's 10 digits. Okay, one more thing we can do. We can talk about generating codes that have letters in them. Okay? So we're gonna do how many, let's say, words. Let's do this. How many 4-letter words Oh, that's bad words. Let's do 5-letter words. How many 5-letter words can you make? Okay, so every time we choose a letter, that's going to be an event. And when we're talking words, let's say we're picking like a password for a computer or something, and we want it to be all letters, okay? So it doesn't matter if you have like X, J, K, L, P or something like that. That's a password, that's fine. So when we say words, they don't have to be actual meaningful words. We're just like basically talking about combinations of letters here. All right, so how many different options do we have for the first one? Well, there's 26 letters in the alphabet, right? And how many choices do we have for the next one? Again, there's 26, 26, 26, and 26. So if you wanted to find out how many, 5-letter words can you make for like a password or something like that, you would use this fundamental counting principle. You would say, well, how many options do I have for the first, or how many ways can the first event occur? How many ways can the second event occur? How many ways are there for the third event to occur? And choosing a letter or choosing a digit or whatever is basically an event. So this is going to be 26 to the 5th power, which is a pretty dang big number. It might even overflow your calculator. Let's find out. 26 to the 5th power. Oh, it's not as big as I thought. Okay, so just if it's 5 digits, just if you're choosing a 5-digit password and it's just letters, there's like 11, almost 12 million ways to do that, which is pretty cool. So fundamental counting principle works for passwords and codes and stuff like that. Sometimes you'll see, like when you're making a password, it'll say like one of your characters has to be a special, or you have to have a special character in your password or something like that. So we can add like numbers if we want or something like that. So let's say how many let's do 6 character passwords can you make if the first character is a number? Okay, so 6 characters. Now each character, as we choose it, is going to be an event, right? It's going to be like one of these kind of things. So choosing how many different ways are there to choose, or how many different outcomes are there for the first character? Well, it's a number, so it has to be a digit between like 0 and 9, because again, we're assuming it's just one character. There's 10 digits that we can choose that are numerical. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There's 10 different ways to have that happen. So I'm not saying that this is not saying that the first digit is 10. This is just saying there's 10 ways to do that. How many ways are there to choose the second one, which is going to be a letter? Because the first one's a number, the rest are letters. 26, 26, 26, 26, 26. So to figure out how many different options there are, we just multiply all these numbers out, which is going to be that 26 to the 5th times 10. So there's another 10 different options. So if we took that number that we got from last time and we multiplied it by 10, we get this. So now we have almost 119 million ways to do that. So that's the fundamental counting principle. Whenever you're making choices or you have different options or whatever, you take each number of options that you have at each choice or at each stage of the game, and you multiply them against the other options at other stages, other choices, to get the total number of unique outcomes.